your program lets you do that. And likewise, there are also non-blocking memory copy routines. So you can see I can pull that data back from the GPU and I'll check later if it's come back. Okay. So you can try and sort of overlap these the memory costs a little bit. You can do synchronization. So that's in C. In Fortran, the PGI version of this CUDA stuff for Fortran, it's really quite simple. It follows the same kind of form. Okay. So it has subroutines which will do allocate and free and memory copies. So it provides you subroutines to do the same thing as the C versions. It has a global attribute and it has the same syntax for yours. Okay. What does that look like? Well, this is pretty much the same vector add we had in C. We can see now it's in Fortran, so subroutine, it's got attributes bracket global here, and then we've got this data structure here, block IDX, so this is the Fortran way of accessing the data structures, and this is how you would call it in Fortran. Okay, so you use a particular data derived type, which the PGI Fortran gives you to create your data structures. But it looks very similar. And likewise with the 2D versions. Value here is, this is to tell the compiler to pass this by, to pass this number to the GPU by value rather than copying it backwards and forwards from the GPU. So it's just a keyword we've added. And yeah, okay. So it's pretty. I mean, you can allocate and deallocate the allocate and deallocate memory. You can use the functions it provides you, the CUDA function it provides you, but it also gives you this thing, this parameter called device. So you can add this to your variable, like say a real device allocatable, and when you allocate it, it will create the memory on the device, not the host. And then when you compile your program, it will check if you send an array as a device array, but you're doing some work with it on the host, not the GPU, it will complain with not compile. And likewise, if you're trying to do it the other way around, if you're trying to use some host data, it's not being called device on the GPU, it will also come to. So it does some check there. But once you've got this device variable set up, you can then copy data between the host and device just using the standard assignment. So you don't have to use CUDA mem copy. You can actually say x equals y. If y is on the device, it will put that. Which is a nice feature for Fortran, but it's also a nasty feature because you can invert and end up copying data backwards and forwards, which is really, really good. So CUDA is a common way of using GPUs, primarily because most of the GPUs we use are made by NVIDIA, and NVIDIA developed CUDA, and that's what they give you in the system. There are other ways of programming GPUs. Okay, so there's something called OpenCL, which is designed to program actually more than GPUs. It's designed to enable you to write programs that work on GPUs and on CPUs and on embedded processors and these kinds of things. In a lot of ways, the sort of syntax and the way you use it is really quite similar to CUDA, but it will go across different hardware. So it means you can use like AMD's, which use AMI's GPUs as well as NVIDIA ones. It has a concept of domains and work items and work groups. So it has a sort of 2D concept as well, like CUDA, where you have groups of work, and then inside each group you have items, and then you have a global domain. Okay, so it's not that dissimilar to CUDA. And then, as before, we're just mapping operations that would have happened, which are independent, but would have happened one at a time on an array or a matrix, and we're mapping them to the individual cores of the GPU. So if we were going to do in C, if we were going to do a similar vector add here, how would you do it in OpenCL? which tells the compiler where this data is going to be. And then we have this get global ID function. So this is very similar to the CUDA block ID, thread ID. Just gives you a way of mapping the data to the clause. One of the areas where, because OpenCL is designed to run on many different devices, not just on NVIDIA CPUs, one of the ways it differs from CUDA is you have to put a bit more effort in the startup and shutdown of your programs, the initialization of your program and shutdown. It's not a hard thing to do, but you have to call a few functions to say, this is a particular device I'm looking for, this is the one I'm working on, have we found it? But because NVIDIA keep CUDA just for their GPUs, then you don't have to do any of that stuff. I'm not going to show you it, but there's a whole bunch of routines you have to call at the beginning of your program. Once you know what they are, it's not a problem, but it isn't slightly more involved with CUDA in that way. And then it has functions just like CUDA does to create memory, release memory, and to copy data backwards and forwards. So you can queue a write between the host and the device, and queue a read between do non-blocking transfers, partial transfers, that kind of stuff. We can skip through these. When we had CUDA, when we were looking at the block ID and the thread ID, you had X, Y, and Z. So for OpenCL, instead of doing X, Y, and Z, you have 0 and 2 for the different dimensions of it. They also have a special set of vector data types built into OpenCL, which may give you better performance and hardware, which has vector instructions in them. So float 4, for instance, or you can do a 4 vector instruction data type. That's more about optimization. And then when we had CUDA, we just launched a kernel by putting those funny brackets around it. In OpenCL, we have you have to enter a set of functions. So set the kernel arguments, then queue the kernel, and then finish queue. So you can see it's a little bit more involved, but I mean, I don't want to overblow it. OpenCL is not hard to program. It's very similar to CUDA, and it lets you go across different. It does let you go across different bits of hardware.
In your CUDA example, you did things in 256 chunks.
Yeah.
Would you have to do the same sort of thing in OpenCL, or is it not?
So the CUDA doesn't care either. It's just that we tend to find those kind of numbers give you reasonable performance across the block. So what we're doing there was say we want to run 256 threads per block. And so in CUDA, in OpenCL, you need to also tell it how many threads per block you want to do. So how many work items per work group you want to make. So you want to say, yes, I want to run 256 for instance. So you could certainly do the same thing.
It doesn't do that for you, you still have to.
You still have to do that. Yeah. So those are both ways when you have to take your code, you have to do some physical change to your code and then it runs system. Which of course people don't like doing. You don't like taking the code and having to write two different versions, one which will run on a computer or run on a GPU. So there is also a different movement to try and get ways of programming GPUs, and that's using directives. Now we've used directives in parallel programming for a long time. Now OpenMP, for instance, is one of the most famous ones. And the OpenMP group are working on GPU directives in OpenMP 4. And the SIMD directives are there on GPU. But the one I'm going to talk about is one called OpenACC, which is a set of directives which are designed to enable you to use GPUs. So the idea here is that we're going to add some stuff to our program, but because it's just directives, we can use the same program on the CPU or the GPU, just depending on how we compile it. If we compile it with OpenACC turned on, it should run on the GPU, and if we compile it with it turned off, it should run on the CPU. So directives, if you never use them, just look like this. So in C, the hash prime ACC, and in Fortran it's exclamation mark dollar ACC. And these are ignored by a compiler who doesn't understand them, but if a compiler does understand them, it'll do something special. It'll do something special with them. Now, not all compilers understand OpenACC. In fact, there aren't that many that support OpenACC at the moment. PGI do, and Cray compiler does. There used to be one called CAPS compiler that has gone bankrupt. GCC are working at the moment on an OpenACC port, but it's not there yet. So, if you've got the and the Intel are also working on it as well, but it's not in their release version as of yet. So although the idea here is it lets you not have to have two different versions of the program, it might restrict at the moment what compilers you can use and therefore what machines you can run. It's a little bit young at the moment, it's still good. So it's built around.
Presumably it doesn't restrict what compilers you use but don't understand them, as it were. So
Yeah.
you could run this code on the GCC on the CPU quite happily.
Absolutely.
Yeah.
Yeah, absolutely. So it just means that you can only run on a GPU system where you have a PGI compiler or a Cray compiler. But yeah, doesn't restrict you other than that. So it's built around, well, slightly complicated. OpenACC has come from Cray doing their directives and PGI doing theirs. So it has two different concepts in it which do the same thing. One is kernels and one is parallel regions. They do more or less the same thing, but they're both there in there. So we're going to say that it's built primarily around this idea of a parallel construct. ACC parallel, okay? And this tells the compiler that anything inside that is going to run on the GPU, and it will do the kernelizing that bits for you. Okay? But the parallel bit by itself doesn't map the work to the cores of the GPU. If you say parallel, then every core will run everything inside it, unless you put something else in there. Unless you put something else in there which tells it how to map the work to the processes. So the primary way of doing that for OpenACC is something called loop. And this is very similar to OpenMP loops. Right? You've seen OpenMP loops, you've seen OpenMP parallelization. You say ACC, OpenACC loop, and a loop on it, and then if that's inside a parallel region, it will take that and try and map it into a sensible way to the cores and blocks of the GPU. And you can combine parallel and loop. But you look something like this: ACC parallel, loop, and loop. And this bit in here, all this stuff in here will run the accelerator, and this stuff in here will be split up across the cores and the accelerator.
So all the stuff we were doing with transferring data items.
So we'll come on to that. We'll come on to that. So by default, anything that's used inside the parallel region is copied automatically for you. Right onto GPU, which is nice in that you don't have to do anything, but nasty in that it could mean you do lots of data copying backwards and forwards because it's not under your control. You didn't ask it to do it, but that's what it to do. So this is an example here. So this is OpenACC. This will work. This code will work. ACC parallel loop. Once where this is in Fortran, but you get the same thing. Input times 2 equals output. And what this will do, this code will do by default, is it will copy both input and output into the GPU at the beginning, run the code, and copy them both back out again at the end. And it will do that for you. So by the time this is finished, your output here will have the right result in it. You actually coincidentally have also copied input twice, which you probably didn't want to do. You can control that, but that's what it will do by default. You can, so by default that loop thing will try and do something clever for you. It will say, I know the GPU you did compiling for, I know it has blocks which have so many cores in it, it has so many blocks, so I'm going to map this to 256 threads and 6 blocks. It will try and do that for you. It's going to try and do something sensible for you, but you can control it if you want to. So you can add things onto your loop, gangs, workers or vectors, which try and map how you map, how many thread blocks you use and how many threads you use in per block. By